if we're thinking about general reactions, reactions that include solutions, liquids, solids, all of chemistry that we care about, and not just gas phase only reactions, we can still start from the same ideas we derived for the gas phase. The key here is that everywhere that we used chemical potential, we now substitute a chemical potential equation that is generic for any phase that uses an activity instead of using the partial pressure. And technically this has a standard state activity beneath it as well, just like we had a standard pressure, right? And just reminding ourselves that AJ is the activity of J. Now, if we have a gas at ideal gas conditions, activity just becomes pressure. And if we have solutions, then we can use the activities that we've defined previously. So our generic equation here, looking at the change in Gibbs energy, we still get the same. So this looks the same as it did before, using the same arguments that we used for the derivation for the gas phase. The difference here is now we have QA instead of QP, where QA we use activities instead of partial pressures. So we get the same form of our reaction quotient and equilibrium constant. Then B raised to the new B. And at equilibrium, this will get a version of this that is Ka, which is at equilibrium. All right, and then we can, we have all the same things. Now, if we as I've mentioned before, if we have a gas, Aj just becomes the fugacity, which is the same as partial pressure for an ideal case. Okay, so gases we've already taken care of. We know how to deal with those. And we get all the same expressions as before. But what about if we have a solid or a liquid, right? So gases we know how to deal with. Let's think about our other phases, our condensed phases. So solids and liquids. What do we do about this? So we still have our, so let's come back to our mu, right, our definition. So for a solid liquid, we can still define the same expression. Our chemical potential is mu naught plus RT log A. We can think about, okay, what's the change in mu? Well, this is a constant, so we're just going to have a change in mu is going to be equal to RT, if we're at a fixed temperature, times the change in the natural log of A. One other thing we can say is that we know that d mu dt, dp, the change in mu with respect to pressure at constant temperature is equal to V bar. This is something we've derived previously. And I'll just reemphasize I said this, but I'll write it down. This is assuming we're at constant temperature. Okay, so we can say that d mu from this expression, d mu is equal to V bar dp. Okay, so then we have d mu on both sides here, and we can equate these things. So we can say that d natural log of A is equal to V bar over RT dp. And so if we want to find what A is, we need to integrate this, or natural log of A, I should say. So we integrate from a standard state where A equals 1 up to some arbitrary value of A, and we integrate our pressure from 1 to some arbitrary value of the pressure. Now the key here is that for solids and liquids, V bar is basically constant. And I'm going to put a mostly here because it's not completely constant, but it's essentially constant. V bar is mostly constant. And what that means is that we can just solve this integral, and we get natural log of A is equal to V bar over RT times P minus 1. So this is integrating some arbitrary pressure, some arbitrary activity from a value of 1. So the 1 shows up here, right, in terms of this integral. And for we get a natural log of 1 term over here that goes to 0 on the left-hand side. Okay, so this gives us an expression that doesn't seem terribly useful. But what we find is that if we plug in values, actual V bar values for for solids and liquids, we get log A will be very close to 0 using this expression. I have an example in the notes of a specific value, which, oh, sorry. I thought I wasn't recording for a second. I am recording. Okay, I thought I would just wasted a few minutes, but I didn't. Anyway, log A is equal to 0, which means that A is equal to 1. And this is true for under almost all conditions, no matter how high you take the pressure, no matter how low you take the pressure, as long as it doesn't start evaporating. For a solid or liquid, the activity is equal to 1. And this is why you learned in general chemistry that solids and liquids do not show up in equilibrium constant expressions. It's because of this. It's because the activity of a solid or liquid essentially stays the same no matter what happens as the reaction progresses. And so because of this, we can say for solids and liquids specifically, in their pure state, A equals 1, and they don't show up in equilibrium constant expressions. So they don't show up in Q or K. Okay, but now you know why. Now you have some justification as to why that's the case, and it's because of this. It's because of this. That V bar doesn't change a whole lot. Let me move this out from behind me. For solids and liquids, the molar volume is basically constant, and because of that, you end up with the activities is staying basically constant and equal to 1 for solids and liquids. In the next video, we'll look at how we deal with solutions, because that's the other thing that really matters for us.